Welcome to Gravitational Field Strength. Here we have the Earth-Moon system, a large mass and a smaller mass. If we look at the Moon's gravitational field in isolation, then we see that it has a radial gravitational field. If we look at the Earth's, that also has a radial gravitational field. These fields are attractive only. But these masses are in close proximity with one another, and therefore their gravitational field lines interact. We can see a more complex version of this up here. There is a point between the Earth-Moon system where the gravitational field strength of the Moon cancels the gravitational field strength of the Earth, and gravitational field strength is 0 at this position. We'll call it point P. To the left, the field lines are pointing towards the Moon, and to the right of this point, they're pointing towards the Earth. On the side of the Earth furthest away from the Moon, the field lines are largely unaffected. And the same is true for the Moon. But as they start to interact in the space between, the lines start being affected. So we get some curvature from the Earth's fields. This is symmetrical. But we get stronger curvature for the Moon because its gravitational field is weaker than that of the Earth. And again, it is symmetrical. As we fill in more of the field lines, this shape starts to become more obvious. The Earth's gravitational field strength is stronger than that of the Moon's, and we can see that because the field lines are closer together. In spaces where there are very few field lines, this is where gravitational field strength is the weakest. Now you have known gravitational field strength as little g so far. It has the units of newtons per kilogram, which is equivalent to meters per second squared. And previously, for example in projectiles, you've treated this as an acceleration. It is an acceleration, but it is also gravitational field strength. And it is equal to F over m. We also know from Newton's law that F is equal to big G multiplied by the larger mass and the smaller mass divided by the distance between the two of them. If we substitute this in to here, then the smaller mass cancels and we get big G over the larger mass divided by radius squared. What this tells us is that at any location within the Earth's gravitational field, we can calculate the gravitational field strength. Note that we've not put a mass here, we are just looking at the location. And the gravitational field strength at this location is equal to big G multiplied by the mass of the object creating the gravitational field divided by the square of the distance it is away from the center of that mass. At location P, the gravitational field strength is equal to 0. And that's because the gravitational field strength of the Moon is equal to the gravitational field strength of Earth. One is pulling to the right, the other is pulling to the left, and they cancel each other out.